Hello everyone. Welcome to week 9 blockchain and its applications live session. So in this session I'll be looking at mainly uh, how Ethereum is different from Bitcoin, the consensus protocol and all those things. And so we'll be looking at this topic. And by the way, sorry for missing out last week's session. I had some due to some unforeseen situation. I had to skip that live session. So sorry. Okay. So tomorrow also we'll be having another live session, and yeah, let's get started then. So everyone knows till now Ethereum has been uh, similar to proof of work, uh, same as Bitcoin, right? But and recently it switched to the proof of stake. Recently it switched to proof of stake. Okay, so we won't be discussing about how it switched to proof of stake, but rather I'll be discussing about the older version of Ethereum, right? The the older version of Ethereum which was using this proof of work. So the proof of work which was being used in Ethereum is not the same as the one used by Bitcoin. Okay, so understanding that proof of work model, and also understanding how Ethereum handled the forks and all those things would it be a bit interesting topic to look into. Like, this is not covered in your video lectures, so it is something that I wanted to share it with you to understand how Ethereum works and how it is different from Bitcoin. Okay, so in Bitcoin the usual one second. So in Bitcoin the usual rule is there is one block every 10 minutes, right? This is the usual rule, and your difficulty is adjusted based on this. So the difficulty as in the proof of work difficulty, how long it takes to compute the hash, compute the nonce such that the hash of the header along with the nonce, right, has is less than some particular number, right? So that difficulty target is adjusted in such a way that over the span of 2 weeks, there's around 2000 odd number of blocks can only be created, which when we divide it, like, to find out one block how much time it takes around 10 minutes. So this is the general rule of Bitcoin. But so this one block every 10 minutes transforms into like around 10 transactions per second, right? But when compared to your common financial networks like Visa, Mastercard, and all those things, right? Visa and all those, your normal banking infrastructure like say RuPay or something, that takes around that supports around like at least 1000 transactions per second, 3000 or more than that, more than 1000 transactions per second. Okay, so for Bitcoin to achieve this speed, right, to achieve this transaction throughput, are basically like two ways to doing it. So the first way is to increase the block size. So currently, I guess Bitcoin has a block size of around like the limit on every block, right? So if you take a block, it has so many transactions, transaction one, transaction two, like that n number of transactions. and how many transactions it can include in a block is limited by the block size. So every transaction, if it takes around say um, like 100 KB or something, at most it can fit in like 1000 transactions also, if the block size limit is like 4 MB or something. And also increasing the block size is um, sort of like you perform a fork actually, and all the nodes should agree to that upgradation. Okay, so this is the first way to increase your transaction throughput. So ways to increase the transaction throughput, the first is you should increase the block size. That is one. So if I increase the block size, we can easily include more transactions. More transactions can be included in a single block, and since we are including more transactions in a single block, the number of transactions confirmed per second will also increase. It will be more than 10 transactions per second. And the second way to increase the transaction per second is we increase we reduce the difficulty. We reduce the difficulty target. And what we achieve by reducing the difficulty target, so if you remember, this proof of work difficulty target is like your hash of the nonce along with the block header along with the previous hash should be less than some target, right? So some number of zeros should be found out. It should be like the most significant bits, some part of that should be all zeros, and basically it means like less than some specific target. And when we so finding out this particular nonce over here, this is what your whole proof of work game is all about. And the first node to find out this nonce which satisfies this condition is the winner, and that block is added to the can be added to the blockchain. So the difficulty target, we should first understand how this target is set. So there is no like centralized way of setting this target, as in like you have a server and then the server communicates with all the nodes. There is no such thing. Instead, the target is set in a decentralized way. Set in a decentralized way among all the nodes, which as part of the consensus protocol itself. And how the target is set is it just looks at the last 2048 blocks, and if case 1, if it has like say um, uh, if it took the last 2048 blocks, if it gets added to the blockchain less than 2 weeks duration, right, then it increases the then it reduces the target, as in it makes it more difficult. By reducing the target, more number of zeros should be there, so it makes it more difficult. And case 2, if it takes more than 2 weeks for the last 2048 blocks to get generated, right, it means that the difficulty has been too high, and the Bitcoin's goal of achieving that one block every 10 minutes, that is not being fulfilled. So if it's more than 2 weeks duration, then your target basically is increased. Your target increases, which means it becomes less difficult, so you can easily uh, find out the nonce. So this is how your target difficulty is actually determined, based on whether based on by looking at the last 2048 blocks, and by looking at how much time it takes for these last for the last 2048 blocks to be added to the blockchain, and based on that the target is readjusted by each and every node independently in a decentralized way. Okay, and all this thing is part of your Bitcoin client code, the code that you have to download in order to set up a node and run, right? All this that code has all these functionality within itself. And now coming back to why we discuss this is the first way to increase the transaction throughput, number of transactions confirmed per second, is we should increase the block size. That is one way, because without by just increasing the block size, you improve the number of you increase the number of transactions that are getting confirmed. Okay, and the second way is when we reduce the difficulty target of the proof of work game, right? By reducing the difficulty target, we basically reduce the time taken for any node to find out the nonce that satisfy this condition over here. So by reducing the difficulty, now what happens is your block generation is much faster, and it will take say if I want to have a block every 1 second or so instead of 10 minutes, you reduce the difficulty and increase the target in such a way that instead of looking at the last um, 2048 blocks or so, you just look at more number of blocks in the past and see whether it's less than the 2 weeks duration and adjust the difficulty in such a way. So by reducing the difficulty, your block generation is faster. So these are the two ways of increasing the transaction throughput per second. And you can obviously combine both both the ways, as in you can at the same time increase the block size as well as reduce the difficulty. Reduce the difficulty target. So both these can also be combined together to achieve a much higher transaction throughput per second. Okay, so this is how the Bitcoin um, can be made faster in terms of how many transactions it gets confirmed per second, and why will and why it's where's the necessity to increase the transactions, because say you have like comparing it with normal centralized financial services like Visa or RuPay, right? It confirms more than 1,000 transactions per second, and if Bitcoin has to compete with these solutions, it has to up its game. And uh, say you want to pay in a coffee shop or you want to pay in a fast food center, you cannot wait for like 6 blocks to get confirmed to the blockchain and then only confirm your transaction is eventually confirmed, right? So all those things cannot be done. So even you cannot in a fast food restaurant or something, with like quick moving, right? You cannot wait for 10 minutes also in order to like see that your transaction is confirmed in the blockchain. And the worst case is, even if the transaction is added to the block, it is highly possible that a fork might occur and that block might be removed from the longest length blockchain. So if it's like say some Amazon website and you are buying some good and the good takes like 2 days to get delivered, right? 2 days for delivery. So in this case, your transaction throughput need not be the transaction finality, as in when does the transaction gets confirmed? How can you be sure that the Bitcoin transaction is confirmed? It's like for sure going to stay on the blockchain. It's like validated for sure. So that you can go with the normal 10-minute one block for per 10 minutes, because in Amazon, say since it's taking like 2 days for delivery, right? At least one day, you can wait for the seller can definitely wait for 1 hour to see that 6 blocks are added on top of that particular transaction, and wait for that finality to get achieved, the transaction finality. And then the seller can then confirm the transaction and deliver the goods. This is possible if the transaction is like some fork happens, and the transaction is deleted or something, as in the transaction is not included in the longest blockchain length. Then the seller can just cancel that sale, cancel that instead of sending it, he can just cancel that delivery and just go on. But whereas if you in this coffee shop scenario or something, right, since your customers are coming in at frequent intervals, right, you cannot wait for 1 hour or so in order for your transaction to get confirmed. And so for all these things, increasing the transaction throughput per second is uh, crucial to support all the normal daily life scenarios. If Bitcoin has to be applicable in all, if Bitcoin has to replace your traditional centralized finance institutions. Okay. So these are the two ways by which we can increase uh, the Bitcoin throughput per second. But the catch is, if we if we do either of these or combine both these things to achieve the throughput per second, there are a few disadvantages. So let's look at what those disadvantages are. So it's not, so why hasn't Bitcoin increased its transaction throughput if it's like been so easy? We'll reason that out. Okay, so we looked at the first way, right? Increasing the transaction throughput by increasing the block size, right? If we increase the block size, what happens is, your validation time increases. So uh, your once your node generates a block, it has to propagate that block to all the other nodes in the network, and all the other nodes. So here actually in the Bitcoin network you have the miner node and the validator nodes, as in those which so usually the validator nodes, the mining nodes will also be the validator nodes. But say for some particular block, one node is the sole miner which mined that block, found out the nonce, and the other nodes should be validating that block and checking whether all the transactions included in that specific block are valid, and it doesn't double spend any previous transaction, all those things. So that all the validator nodes would be checking. And note that only the miner node will be getting a reward, um, and the validator nodes are not rewarded, right? All the nodes should be validating the block which is being propagated by the miner node, but only the miner node is rewarded because it is only solving the proof of work, whereas the validator nodes are just validating all the transactions and the rules, the consensus rules, as part of the Bitcoin protocol, right? But now, if we increase the block size, the time for validation increases, and any and the resources required for the validator nodes, the storage requirement, and also the time taken for validation, that will increase proportionately, and um, that would be a problem because some nodes, like some validator nodes, like our light nodes, as in they don't have much of computational resources, and they just wanted to take part in the validation process. And now, if we increase the block size, they would be they would have to spend more money on buying those resources for, like, since like the block size increases and all those things, right? Since the lightweight nodes are having a constraint on the storage requirement and the computational requirement, right? That would be like a drawback. The second drawback, when we increase the block sizes, there can be a delay in propagation of the blocks, right? Because now instead of sending like 2 MB block, you would be sending like 4 or 10 MB, and you can be greedy and increase the block size to like 1 GB, because sending 1 GB to all the nodes, to all the other nodes in the network, right? That would take lot of time, and we can be sure that all nodes have the same proper network bandwidth and all those things, and that will lead to network congestion. So these are the two advantages when we look at increasing the block size to improve your transaction throughput per second. Now let's look at the second way and what the disadvantages are. The second way to improve the transaction throughput per second, which we had discussed, is reducing the difficulty. Reduce the difficulty, uh, uh, reduce the difficulty level, right? So why was so why did um, Bitcoin in the first place have like 10 minutes per block? Why didn't it reduce the time or make it like 100 minutes per block or 5 minutes per block? And the reason is it was just like a trade-off. As in, if you reduce the difficulty level, okay, then more number of uh, blocks would be created, because it becomes easier for the miner to solve the proof of work solution. So it becomes easier for the miner. And now what happens is, more miners, say in like say for a particular block, say in round 10, for block number 10, there will be like say 100 miners now would be able to solve. So previously, say when we have this 10 minutes per block condition, like some number of zeros, the difficulty target, that condition, right? If that was the difficulty level, and now if we reduce that difficulty level, it becomes easier for the miners, and now more miners would be able to solve the proof of work, and each of those miners would be um proposing block 10. And now what happens is, when more than one miner proposes the same proposes like a different block in the same round, right? So say like miner 1 proposes block 10A, and miner 2 proposes block 10B, so on. What happens is, in the existing blockchain, miner 1 will be added over here, B10A. Here it will be like B10B, so on. So there will be like the magnitude of forks will increase a lot. And now what happens is, you have reduced your difficulty level and improved the number of blocks that are getting added to the blockchain. More the miners would be able to participate, more number of miners, but the catch is, there will be more forks occurring, and now to resolve the forks, time wasted on reorganization. So say like initially this is your blockchain, and now more many nodes have created, have uh, solved the proof of work solution and created like multiple blocks, means now on top of this Let me just use a different thing. Say it has created a fork. Now some nodes would look at this particular as the longest chain, and it's keep on adding blocks onto this green block, whereas some nodes would have received this red block previously and would start adding on this red block. And now what happens is the time for the fork, or since like even the nodes with smaller mining power would now be able to easily find solve the proof of work and propose new blocks. The block proposing period would be reduced drastically, but the probability of forks increases a lot, and so it will be like a bit complicated. And finally, what happens is only the longest chain should be used for should be considered, and all the transactions on the longest chain are only considered valid. But to find out the longest chain, you have to there'll be like multiple longest chain, and to resolve a fork means eventually one chain would increase in length eventually, and that can be considered as the longest chain. But now since like more forks are occurring and all the nodes are easily proposing new blocks, the time to resolve a fork, as in the time for a particular chain to become the longest chain, will increase so much. Your transaction finality will be will be increased a lot. So transaction finality, as in, since say like if I have a transaction over here, transaction 10 is being in this specific block means, I should be sure, since like blockchain is supposed to be immutable and like an up and only ledger, if this transaction 10, once it is added to a block, I should be pretty sure that this block is not is always part of the longest chain for the transaction to be considered valid. And due to some fork occurring, and if if the red chain gets becomes the longest chain, then this green chain is not the longest chain, and all the transactions in this are orphaned out. So transaction finality is sort of the minimum amount of time that I should wait for in order to confirm that the transaction will always be part of the longest chain, and the probability of that transaction being orphaned out. Hello, yeah, hello. Hello, did anyone have any query?
Sir, I have a doubt, sir.
Right.
Hello, sir.
Yeah,
Sir, 29th is our blockchain examination, sir. Like,
you are asking the exam date. I'm not sure. I can.
okay, sir. Okay, exam is okay, sir. Is the exam is multiple choice questions or you have to write theory, sir?
I'm not sure of the exam pattern,
Okay, sir.
but mostly it will be MCQ
Because
or
MCQs. Okay, sir.
just small paras. I'm not sure. Uh, the last time it was
No, sir. It
MCQs.
actually comes under like a computer science and engineering like category, sir. So my friends are writing exams like under whatever comes under computer science and engineering. It's all multiple choice questions.
Right. So when I took NPTEL exams, it was MCQ or the numerical answer had to be filled in. So,
Oh, okay, sir.
right. Okay. So coming back to our discussion, right? So when we reduce the difficulty level, the probability of forks happening is much higher, and this affects your transaction finality. So by transaction finality, it just means that the time we should wait, the waiting time to ensure that a specific transaction is not orphaned out. so it's not orphaned. So this is the transaction finality, and currently at having 10 minutes per block, right? 10 minutes per block, it is enough if I wait for 1 hour, because like 6 blocks are getting added on top of the blockchain, and so 1 hour, like 6 blocks, and once 6 blocks are added on top of a specific transaction, I can be sure that the probability less than like 0.0001, like that also, my transaction would not is permanent in the blockchain. It won't be orphaned out in the future. So this is transaction finality. And now if forks are occurring, more number of forks would be occurring because the difficulty level is reduced. So if the forks are occurring, right, the time for every node to communicate among themselves and find out which is the longest chain would take much more time, right? All the time would be wasted on that reorganization and finding out which chain should be considered a longest chain, and uh, don't be constructively used in solving the proof of work challenge and proposing new blocks. So initially, when it was like 10 minutes per block, most of the computational resources and the time spent would be for proposing a new block. Whereas in this scenario, when we reduce the difficulty, it will be the inverse. So the time spent on communications between every node to find out I'm on, say like node 1 would be telling I'm on this green chain and this is the longest chain, whereas node 2 would be telling I'm on the red chain and this is the longest chain. And by the time the communication is over, since the difficulty level is pretty low, some other node would have added a block onto the green chain, and now that would be a longest chain. And by the time that the nodes following that green chain propose to the nodes following the red chain that the green chain is the longest chain, some other node would have added to the red chain. So this type of conflict would be going on due to the low difficulty level, right? And this from a security so from the transaction finality perspective, it is a drawback, because now it will take more time for you to um, ensure that your transaction is not orphaned out, because every node can easily add a new block, or like fork the chain and keep on adding new blocks, right? So that is a drawback when you reduce the difficulty level. So this 10 minutes per block is kind of a trade-off taken into consideration based on how often the forks happen, and also the time taken for communication among all the nodes, as well as like a reasonable difficulty level, so that miners with some considerable amount of resources can actively take part in the mining process, right? Because like the proof of work mining is also sort of economic um, incentive, like economic investment um, done by the miner, because now since the miner has invested so much of the computational resources, he is bound to propose valid blocks, right? Whereas in if we reduce the difficulty level, the threshold for a node to become a miner is reduced drastically, and now like any miner with just a laptop or so, they can, any node with a laptop or with like less computational resources, they can act as a miner, and the mining space would be too congested, and the economic investment, right? How are we sure that a miner won't behave badly? Like if he behaves in a dishonest way, the miner has too much to lose, because he is losing on the wasted electricity and the wasted computational resources and time. But now if we reduce the difficulty level, the miner, even if he tries to do like a double spend operation or something, uh, the electricity wastage and all those things, because the difficulty level is reduced, is not very significant, and this is sort of like against the Bitcoin's security policy. So these that we looked at two ways of how to deny ways of improving transaction throughput per second, and found out that it cannot be applied directly to the Bitcoin protocol, because applying it directly has introduces new drawbacks which affects the transaction finality, and also eventually it will affect the transaction throughput, right? So then how can we improve the transaction throughput per second? And the other third disadvantage, which is sort of hidden, is called as mining centralization. So when we reduce the difficulty level, right, and improve the increase the block size in order to increase the transaction throughput per second, it leads to mining centralization. And what that means is, um, say you have so this is your blockchain, okay, and now since your difficulty level is too low, uh, some node would be proposing this block, would be like proposing the red block chain as the longest chain, whereas some node would be proposing this green blockchain as the longest chain, and there would be a competition between these two chains, right, this red and green chain, because like some other node would be adding on top of this, whereas another node within a few seconds or so would add on top of this block. So there will be a competition, but what an attacker can do is, so the time for resolving this fork is mainly because every node has to communicate with all the nodes, so this communication cost is very high in Bitcoin network. Since the nodes are distributed all across the world, time taken for the nodes following the red chain to tell the nodes following the green chain the to resolve which one is the longest chain, the communication time would be very high, since like new blocks would be would be simultaneously added while this communication process is going on among the nodes, and there won't be a clear winner. Now what an attacker the attacker what they can do, the attacker as in a dishonest mining node who wants to say double spend, as in like invalidate, say like attacker had um, transferred some bitcoins to some seller, right, and say that is transaction 4 or something, and that transaction 4 is present over here. The transaction 4 is present in this specific block, and now the attacker wants to double spend it, as in like this transaction 4 is using the output of transaction 2, and now the attacker wants to add a new transaction as in transaction 5, where he just spends that output to himself, to their account itself, and just redirecting uh, the bitcoins. So basically he wants to add a new transaction 5 where he just uses transaction 2's output and sends the bitcoin to some other account, and the attacker's final goal is to ensure that transaction 5 is validated and part of the blockchain, and not transaction 4. So that is the goal of the attacker. Now what an attacker can do is, since my difficulty level is reduced, the attacker can now easily produce more blocks. Easily produce more blocks, right? And now what an attacker can do is, when this competition is going on between harness nodes on which the red chain or the green chain is the longest chain, the attacker will not communicate with other nodes. Instead, the attacker will just use, since the difficulty level is low, right? The attacker won't communicate with the other nodes. The attacker will just start creating a chain, as in it will just create some 7 blocks or something, and all of these blocks would be valid only. And among these valid blocks, your transaction 5 would be also inserted in one of these blocks. And now this this full 7 blocks over here, while constructing these 7 blocks, so usually in the Bitcoin protocol, once if I construct a block, um, the block should be propagated to all the other nodes and it should be validated. That's the that's the protocol that is assumed. But what the attacker can do is he can locally construct these 7 blocks. And once the attacker gets to know that okay, the red chain has only like 3 blocks, the green chain has only 3 blocks. At this time, what the attacker can do is he can release these 7 blocks to the network at the same time. So release it at the same time. And now what happens is when all the other nodes, so this blue block would be the would be pointing to this over here, to this block. So basically, if I just redraw it, this is my original blockchain, on top of which there are like 3 red blocks, 3 green blocks, and the attacker at the right time he has just released like 7 blocks. Okay, and now any honest node, if they look at this, so here transaction 5 is included in this green, transaction 3 is included over here, and the attacker wants to delete this transaction 3, transaction 4 I mentioned, transaction he wants to delete this transaction 4. Okay, sorry. So he wants to invalidate this transaction 4 and make sure this transaction 5 is not part of the longest chain. So now the attacker would locally construct all the 7 blocks, and the right time would release all the 7, propagate all the 7 to all the nodes. And the other honest nodes, what they would be doing is once they create a red block, they would propagate to all the nodes. Once they create a green block, they will propagate to all the nodes, and there will be a competition to find out which one is the longest chain or not, right? But whereas the attacker would be like sort of like selfishly, right? Selfishly, the attacker would be mining all the 7 blocks locally without sharing the block status with the other nodes. And when he has extended, when he has increased the number of blocks that the attacker has mined over some period of time, like 7 blocks or so, compared to the current longest chain, which is 3 blocks, he will then release all the blocks now and propagate to the other nodes. Now the other nodes would look at the red chain, green chain, and the blue chain, and see that the blue chain is the longest chain by significant number, and all the nodes will now start working on the blue chain, and these the red chain and the green chain will be orphaned out, and your transaction 4 is orphaned out because the block containing transaction 4 is removed, and transaction 5 is the one which is included in the blockchain. So this is sort of like a, not exactly, but this sort of like a selfish mining strategy where the attacker selfishly locally mines the block, and and at the correct time he just uh, releases, propagates it to all the other nodes in the network. And so selfish mining is can be done in a normal scenario also, but specifically when we reduce the difficulty level of uh, when we reduce the difficulty level in order to increase the transaction throughput per second, uh, the the threshold for a mining for a miner to have this sort of to have this sort of strategy to perform double spending is reduced. Okay, and the other thing is, since now difficulty power is reduced and like nodes are taking more time for reorganization, uh, there are so the security property of the assumption of Bitcoin is like 51% hash power, right? Hash power should be honest. But now, if your difficulty is reduced, the time taken for this sort of selfish mining strategy or the hash power that is required is now reduced to around like 20%. So, like a node with 20 to 30% of the hash power, which is easily achievable in current computational resources availability scenario, this 20% hash power is easy to achieve because like take example for your mining pools where you rent out your computational resources, like a group of miners come together and try to form a mining pool. Also all these mining pools will now yield a tremendous influence, and this sort of strategies they can undertake and ensure that they get the maximum profit because their chain would be the longest chain and their miners would be the ones that are rewarded. So that is the problem with mining centralization, and becomes a lot easier when we reduce the difficulty level of um, reduce the difficulty level in order to achieve a higher transaction throughput per second, right? So this is the disadvantage. So now, so we have looked at two naive ways, and there are so many disadvantages. So now, how can we then improve the uh, block number of transactions per second? And for that, Ethereum, so how does Ethereum try to improve that? And the other thing is, in Ethereum, it's not just only a financial service like Bitcoin, where you just have like Bitcoin as the cryptocurrency, uh, and transferring from one account to another. That's the main usage of Bitcoin. Whereas in Ethereum, it sort of like introduces the concept of decentralized applications where you are having your smart contract, and all the whole the blockchain itself is like sort of a universal computer. The Ethereum is like a universal computer which executes the smart contract and ensures that the result produced by that contract is uniform across all the nodes, right? So in that case, when you have to say implement a decentralized application, so instead of like a centralized social media platform, you want to have a decentralized social media, then every um, transaction or like interaction with that decentralized application, so every interaction with the D app, with the decentralized application, all the smart contract, right, is in form of like a transaction. It's a transaction actually. And by the term by transaction, what we mean is it's eventually submitted in a block. It's part of a block, and that block would get um, added to your blockchain, right? And now, if our transaction time for it to get confirmed is like for block to get confirmed is 10 minutes, similar to Bitcoin, then the efficiency of your application is very less. is affected, especially in the case of Ethereum, which is projecting itself as a decentralized application platform and not as a cryptocurrency, right? And so Ethereum is more uh, should somehow improve the transaction throughput per second. So what Ethereum does is, instead of increasing the block size naively, right, and reducing the difficulty, all these things, it follows something called as the ghost protocol, like a ghost sort of protocol, not exactly ghost, like ghost sort of uh, protocol. So what we mean by ghost is actually like greedy, heaviest, sub 3. Okay. So usually, so in this mining centralization, right, what we discussed, which one is the longest chain? Wait, let me draw it over here. So, say if we have something like uh, this. Okay, so this is your blockchain, and this one is provided by the attacker following the selfish mining strategy, whereas the red and the green blocks are the ones which was done in a honest way. Okay, now just following the longest chain policy of Bitcoin, the blue chain is the longest chain, and this will be considered valid. Whereas in the ghost sort of protocol, this sort of so instead of blindly just counting the number of nodes in a chain and terming that as the longest chain, what the ghost protocol does is it looks at the the sibling nodes also, as in like say so it will look at the orphaned out blocks also. The orphan include the orphan blocks in the weight calculation. As in, if a particular block has more number of children, so if I start from this block over here, this block has one child only, and now if I come to this block has like three child. Okay, this not like four, but now if we come to like so these two blocks are confirmed, as in there are no like forks or like no other blocks is at that same height. Whereas if we come to this particular height 3, right, which block should be included at height 3, right? Now what the longest chain will do is, okay, I will look at the chain in which each block is included, and whichever is the longest chain, I'll include that block. So in longest chain, when it will select the blue block because it's part of the longest chain. Whereas in the ghost protocol, what will be happening is it will look at which among these three blocks, say this is 1, 2 and 3, which among these three blocks has the most children, right? So in this uh, in ghost protocol, this green block would be selected, right? This green block would be selected, and now again out of in this specific so at height 3 this green block would be selected, and now in height 4, out of these two blocks it will check which one has the uh, more number of blocks splitted out, or like as a child, as a parent, which one has more blocks. So finally what happens is, in the ghost protocol, I just so this will be your longest chain, whereas in the ghost protocol this specific would be your longest chain, because instead of just blindly focusing on the longest chain, um, this whole thing would be part of your blockchain, not just this, but also so this whole part would be considered as part of the blockchain. But out of, one second, not exactly this. So we have this, and this. So all these five blocks in the green chain would be considered a longest chain according to the Ghost protocol, compared to the naive longest chain solution. The reason being, uh, if you look at the red chain is like just two blocks, and let's leave that out. By default, it like has two little blocks, the chain height also. Whereas if you look at the blue chain, right, it can be highly possible that some attacker or something has done like a selfish mining strategy to come up with these many blocks. Whereas if you look at this green chain, right, you have like so many forks happening, and there is like a high possibility that it's not just one node, whereas multiple nodes were trying to propose new blocks. Because of that only these many forks had occurred, and um, so more number of nodes are participating in these in this specific green chain. And so to add weightage to that aspect, the ghost protocol, instead of blindly looking at which chain has the most number of nodes, it looks at the chain which at each level it selects the block which has the most children, so that the credibility of adding that block to the blockchain is much higher. Say like if you consider this green block over here, this green block, right, compared to the red and the blue block, so this and this green block had been propagated to more nodes, and that is why those nodes kept this green block as a parent and added their corresponding blocks on top of this parent, right? So like more nodes got hold of this specific green block, say G1, and added G2 and G3 on top of G1, right? So more nodes got hold of that green block, and it was like more widely propagated. And now say if an attacker has to, like if we are following the ghost algorithm, and now if we say the attacker has to do a double spend operation, he just doing like a selfish mining strategy by coming up with these many blocks is not sufficient, because it's not enough, because instead of coming up with this uh, blue chain, the attacker now has to come up with a chain something like this. because like your ghost protocol gives weightage to the number of child nodes pointing back to the parent. It gives weightage to that, right? So the attacker should come up with uh, a chain in such a way that this the number of at each node at each block height, the parent block has more number of child blocks when compared to the valid chain. So instead of having like a longest chain like this, right, the attacker has to come up with this sort of some chain having this structure, and then only the ghost protocol will consider this as the most weighted chain. Okay, the most weighted chain, and it will consider this as the valid chain. Okay, and the reason why this is not very profitable for the attacker, not profitable for the attacker is because, say in this longest chain scenario, by just easily forming the longest chain, he can now um, the attacker can now uh, receive rewards for each of the blocks. So like 7 blocks he has added, so he will get like 7 into 12.5, around like 84 bitcoins for sure. Whereas in this weighted chain scenario following the ghost algorithm, uh, the rewards he won't be getting for the rewards would be getting like out of this chain structure. Only one chain would be the longest chain in this actually. So one small um, like uh, one small detail is that the whole of the green chain would be part of the weighting score, the score required to calculate the longest chain. But eventually, like out of these green blocks, which one is the longest chain, that would be considered valid, whereas the other blocks would be considered as would be considered in the scoring scenario, right? So this weighted chain, this ghost algorithm, if the attacker has to follow and form a chain in this structure, right, the longest chain would be like pretty low, and also it's not profitable for the attacker. Plus all these blocks, right, this block, this block, this and this, all these are actually not part of the longest chain within this chain structure, and they won't they these all are not actually rewarded. Okay, and also it it prevents the attacker from doing, not prevents exactly, but sort of the attacker is now forced to communicate with the other nodes. If he has to come up with this structure, right, he has to do it like willingly, or he should be like, the attacker should be clever enough to form this structure. And also it might be highly possible that some other the other honest nodes can come up with a more complicated block structure, like say one with having like 5 children or something, right? Because like since your difficulty level is reduced, um, it is highly possible that more number of forks can increase, and in a natural way, of course, these forks will increase naturally, and a node with 5 children is of course possible. Whereas now the attacker should somehow find out what was the number of children added to this parent block and try to increase that count in the attacker's own structure. And for that, the attacker should communicate with the other nodes, and this will be against the selfish mining strategy which the attacker has used, because in order to form this longest chain, in this longest chain scenario, the attacker did not communicate with the other nodes, whereas in this scenario, the attacker is forced to communicate with the other nodes, right? So this is what Ethereum does. It performs like instead of having this longest chain and following it blindly to find out which is the valid chain in the whole blockchain structure, it uses this ghost protocol where at each block, right, it looks at how many nodes are its children and follows that part, and the longest chain in that specific part is the valid chain, right? And couple of things which Ethereum adds to this ghost algorithm is one, say usually the fork blocks are not awarded in the four orphaned out blocks are not awarded. So, right, so say like you have a blockchain something like this, right? And so out of this, this will be your so in this level this is selected. Okay, so this block is selected, and out of these three blocks, this block would be selected because it has two children compared to like um, so let me go in this way. So say like this has three children, and now this has like two children. So now actually this block is selected, and now this block would be selected because it has three children, and out of these three blocks, this block would be selected and this block. So finally this all these three would be the longest chain and not this one. So this is not the longest chain, this will be your longest chain. And how it arrived at this longest chain is because these are all like sibling nodes, right? So sibling as in like uh, uncle or so your father it's called like boomer nodes, I guess. Boomer is like a gender neutral way of specifying uncle or like aunts. Okay, so siblings of your parent. So by sibling, as in like this is a sibling node, this is a sibling node with respect to this specific block. Okay, so these are all sibling nodes, and right. So now actually. Um, This is the longest chain according to the Ghost protocol, according to the Ghost algorithm. But how it arrived at this longest chain was because of all these nodes that were calculated as part of the the weight score, right? Because like you had initially these blocks, or this green block, this block, and this block, everything was considered as part of your score calculation for a specific block. Because like if I have to select this parent block, I looked at the four children, number of children it has, the child blocks, and that's why I selected this block. And even though this is the longest chain, the other blocks were also considered during the score calculation. So forks occurring um, so when we consider this as the longest chain, right? What do we mean by longest chain in this ghost algorithm is the transactions in the longest chain are only valid. The transactions um, in this block or the other blocks which are not part of the longest chain, they won't be validated. As in those transactions should be orphaned out and they should be added to some other block as part of this longest chain. But those blocks would be part of the weight calculation in order to prove that this set of four blocks is the longest chain, right? And right, but now um,
what Ethereum does is, uh, it's not just provides rewards for this longest chain blocks. So usually like the mining reward is given to the longest chain block, right? So this block, so all these blocks highlighted in this blue, right? These four blocks would be getting the mining reward because they are part of the longest chain. Whereas in order to incentivize the nodes which form these the other green blocks, which are all part of the weight calculation in order to find the longest chain, right? All those other nodes will also be getting partial rewards. So say like 5 eters or something is the block reward, means they will be getting like one reward, 1 ether each or something like that. So they will be getting partial rewards in order to incentivize the nodes that are forming these orphan blocks. And what happens is, what's the reason behind this approach is, in order to prevent this type of like selfish mining strategy, where if we don't communicate with others, we save on communication cost time, and we can spend more resources on um, finding out on mining new blocks. To prevent that sort of attitude by a mining node, if a mining node is adding its block to the blockchain, and if it even if it turns out to be an orphan block, if it's part of the longest chain substructure, right? As in say like here, if you have another say if I just use a different color, okay, and say if I have another node over here, oops, say use both. Say if I have another node and some node or some block, and it splits like this, and this has just only like one child only, right? So all this structure, this full green block structure would be considered, right? So the nodes which supports this weighting score. So like this green block was selected. Say this is G1 means. So this G1 was selected because it had 3 children compared to the purple block having one child. Right. So since all these nodes were part of that weight calculation scenario, which eventually paved way for selecting these four blocks as my longest chain in the blockchain. So all these blocks, the green blocks, would also be rewarded with partial rewards. And the nodes which mine those would be getting the partial rewards. And this is in a way incentivizing the mining nodes to communicate with others and mine new blocks whenever possible, and not selfishly keep it local, keep it in a local fashion, and suddenly like propagate throughout the network in order to reap the most benefits. So say if I'm a honest node, I'd be mining like this block, like G1, and also like some this block over here. And finally, like one of my blocks is only included in the blockchain, in the longest chain, but the other blocks is supporting that longest chain by adding to its weighted score. And because of that, I'll be receiving the full mining rewards for the block that I had added in the longest chain, as well as for the orphaned out block, which is supporting the longest chain by that weighted score scenario. So I'll be getting more rewards, and the attacker would be missing out on these extra rewards if he is not if the attacker is not communicating with the other nodes, right? So that is the so in this way what happens is, um, you can reduce your difficulty level, right? Reduce your difficulty level also, but to uh, to deal with the selfish mining strategy, and ensure that even if the number of folks increases a lot, it actually improves your security. So forks happening in the ghost algorithm improves the security of the blockchain because those forks are not orphaned out fully. Not orphaned out, but they are eventually considered as part, considered in the weight calculation scenario. Considered in weight calculation. So in this way, the forks are not completely a waste, whereas it is rewarded by with partial rewards, and this is in a way dealing with the drawback which we had discussed about uh, reducing the difficulty level to improve transaction throughput per second. And in Ethereum, how it works is when I propose a new block. So when you propose a new block in Ethereum, so in Bitcoin you usually have this nonce field, you have the timestamp, and you have the previous block header in Bitcoin. Apart from these, uh, so apart from these fields in Ethereum block, you will have something called as the rumor list. Spelling I'm not sure, but so this is something like siblings of your parents, of your ancestors, of the ancestor block is included. See, so what happens is, say if I'm proposing a new block, say B5, means you the nonce would be calculated based on the previous block B4, and also you would be pointing to other blocks, say like it has like B3, and then say this is like B2, and B2 has like B6, and something like this means, right? And what you will be doing is you will be including the B5 block which you are proposing, which you are mining. B5 B5's rumor list would include B3 as well as B6. Okay, so the more number of rumor blocks it can include in the block, include in its list, include in its list the B5 block, the more uh, weightage it is providing to itself, because it's a way of showing that I'm having I'm including all these blocks in calculate my score, like the block score, right? And it is in a way showing that I was not acting selfishly, whereas I was communicating with the other nodes, and I, because of that only I was able to find out like B4 has these sibling nodes B3 and B6, right? And when B5 is eventually part of the longest chain, what happens is how the B5 block, the miner node is rewarded is, the miner node is rewarded for B5, the B5 miner, how they are rewarded is like they get the full block rewards for B5, say like it is 5 ethers, right? And they would get uh, I guess uh, 7 by 16th or something, some ratio. So like out of, so say adding a full block is 5 ethers means B5 miner will get 5 ethers plus fraction of the 5 ethers with respect to block B3 plus block B6, right? So 5 ethers plus 1 ether or 1 ether, something like that, B5 minor would be getting, and the block B3 and the B4 minor, they will be getting some fraction of the 5 ethers. So in a way, um, this sort of strategy, the reward strategy and also the ghost algorithm, what it eventually achieves is, even though I reduce the difficulty level, um, the nodes are incentivized to communicate with others, and it's not a problem if forks increase, but also but I'm utilizing those forks in a way which improves my security and makes it more difficult for the attacker to act selfishly and uh, disturb the uh, 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 to disrupt the security of the blockchain by forming a longest chain in a local fashion or something like that. All those strategies are made less approachable, or like it's made more difficult to stage by an attacker. And also now, since like the B5 miner has to communicate with the other nodes to find out what block B3 was or block B6 was, and this is in a way is not like the attacker is not the B5 miner is forced to communicate with the other nodes, and by communicating with the other nodes, and if he's including the sibling blocks in the Umer list, he is actually increasing the reward that the minor node would be getting, the B5 minor node would be getting, versus a solution where you don't include any sibling blocks in your Umer list. So you'll be getting less reward. You'll just be getting your own block reward. Whereas in the B5 minor scenario, you'll be getting a fraction of the B3 and B6 rewards also. So it is more uh, economically uh, incentivized to communicate with the other nodes. And Ethereum has to prevent um, uh, so Ethereum has a way of has a limit on the limit up to which you can include your include a node as the sibling node. So this was considered after many studies. So up to what level? So say if I have a chain like this, right? So now if I want to add a new block over here, uh, which all blocks should be considered as a sibling block? Up to what level can I consider? Can it be considered? So out of this, this block can be considered, and if I and also say like over here, if I have it like this, and now this block can be considered, and this block can be considered, right? So if I limit, so up to what level is up to like 7 levels or so, I can consider the sibling block. Whereas if it's just like limited to 1 level or 2 level, right? Now the competition for um, so one thing is your the transactions which are included in block B3 and B6 are not validated, right? So you can just mine a new block like B3 and B6, and say like the B3 block miner and B6 block miner could have included the their blocks on top of B4, but instead of doing that, they just added it on top of B2 itself. One reason is like they need not include any transactions within their blocks. The transactions can be like invalid transactions also, but your block header should alone be valid. That's it, right? Because anyway, my transactions in B3 and B6 won't be counted, and only the B2, B4, the longest chain in this structure would only be counted as valid transactions. But B3 and B6 would be considered to find out which one is the longest chain, because like the more number of children, that criteria. And so nodes, right, the mining nodes can um, spend less computational resources, and if they are happy with just this fraction of reward that they will be getting, if say some node includes their block um, as a sibling block or something in the Umar list, they will be getting a fraction of reward. And if they are happy with that, instead of mining on the longest chain, instead of adding on top of B4 and B5, they will just be adding on top of a block which is not at the top of the longest chain, whereas say instead of adding to B4 and B5, it would be adding on top of B2 in order to be included in the Umar list of B5. So this sort of like a strategy where they don't want to waste significant resources and validate every transaction and add it in a block, whereas they can just, if they are happy with the fraction of rewards, they'll try to be as sibling blocks itself throughout. They'll be trying to find that sibling blocks alone. And in order to avoid that sort of strategy and force everyone, their goal should be to mine on the longest chain. And even if after mining on the longest chain, if they turned out to be on a 4, then the fraction rewards. um, so like there are two goals in Ethereum, right? So one, everyone should mining new blocks and communicate with the other nodes. That is one. That is one goal. And the second goal is mining on the longest chain is preferred, because finally the longest chain is the one where your transactions are getting validated, and all those transactions only reflect your blockchain, right? And if the nodes don't want to waste their resources, and if they are happy with that fraction of rewards they get being the sibling node, they won't be mining on top of the longest chain, whereas they'll be happy if their block is added in the boomer list. So accordingly, instead of now adding on top of B5, they will be so instead of adding on top of B5, they'll just add on top of B2 itself, say like B7, such that some other block will include B7 in zoomer list, and it will get a fraction of rewards for B7. So to avoid these things, the mining Ethereum has a limit of up to 7 levels, as in like up to 7 level of siblings only I should be adding. And also like if I if like the number of and also like so by placing a limit on this number of levels to be considered for a sibling, right? Eventually a node, um, the mining node eventually would be forced to add on top of the longest chain in fear of not in fear of crossing that level limit, right? So this Ethereum has this limit, and it also uh, has this follows a sort of ghost algorithm to make forking much more safer, and rewards the orphaned blocks also by adding it into the longest chain calculation procedure. And you can you can ask a query like why can't we include the transactions which are orphaned out but also part of the blockchain structure to find out the longest chain which supports the longest chain. The reason is, now if you don't have like a single longest chain, right, how do you ensure double spending does not occur? And the whole process becomes a lot more complicated, and the validation rules becomes a bit messy. So to avoid that, uh, they just consider the transactions in the longest chain alone, and the other blocks which support the longest chain are partially rewarded, but their transactions won't be validated and is not reflected in the blockchain state. So this is how Ethereum tries to solve Ethereum's consensus protocol is different from Bitcoin, and it tries to improve the transaction throughput per second. So any doubts in this uh, explanation till now I have given? So this is what I wanted to cover in this live session, and I hope you understood the key takeaway from this live session. How what are the naive ways of improving transaction throughput per second, and what are the drawbacks in doing that, and how Ethereum tries to um, um, transform those drawbacks into sort of like a um, advantage, and improve the security, and also like um, make it more unfavorable for the attacker to stage a selfish attack. Any doubts? Okay. So if you don't have any doubts, then we can end the session. We'll meet tomorrow at uh, during the live session. Thank you everyone for attending the session. If you have no doubts, we'll end the session. Thank you everyone. I'll just wait for a minute or so. If you have any doubts, you can unmute yourself and ask. If not, I'll just end the session. Thank you.